Okay, perfect. Right. Okay, so let me start by thanking Eduardo and also Irene and Miguel for letting me speak in this series and also for organizing this series. It is really nice, and I recently started attending it. And today I will I probably hear someone typing from the audience. It would be nice to not have that background noise.
Yeah, sorry.
Thank you. That's much better. Yeah, so in this talk, I will explain you what so the content of this paper that I have put out last year together with Ivano Basile, who is probably already connected. And so I will talk about this specific paper, but I will make sure to start with spending some time on the motivation, since this is part of a larger research line that I have initiated and I'm trying to push with Ivano. And it is, as the title states, about asymptotic safety and the Swampland. So big starting motivation is that essentially the proliferation of approaches to quantum gravity started, if you want, originally from an incompatibility between unitarity and renormalizability in the perturbative quantization of general relativity. And this resulted indeed in a proliferation of approaches to quantum gravity that I pictorially represent here. So this is obviously not supposed to be precise in any sense. This is a pictorial representation of how different approaches moved from the origin of this big theory space in different ways. So for instance, advocating to new physics or new principles, or by relying on non-perturbativity, by introducing new symmetries, and so on and so forth. But at the end of the day, any approach to quantum gravity would like to be consistent according to some criteria, for instance, unitarity, perhaps normalizability, even if, as far as I understand, is not a common trait of many of these approaches. And definitely one would like to make contact and reproduce observations on large scales. And if we also want to be ambitious, we also would like to make predictions in quantum cosmology, black hole physics, scattering amplitudes, and so on. The focus of this talk and the focus of the Swampland program is about consistency. So what are the criteria that effective field theories coupled to gravity have to satisfy in order to be consistent with an ultraviolet completion of gravity. And this is the starting point for the Swampland program, which to my understanding aims at being in principle independent of the specific ultraviolet completion, specific of the specific quantum gravity model, but aims at identifying a certain number of universal consistency criteria, identifying the so-called string landscape. And it is true that so Swampland criteria are mostly tied to string theory, in particular in supersymmetric constructions, and they are partially inspired by string theory. But some criteria also are more general. They are on solid grounds, being tied to black hole physics and cosmology. And they have been tested widely within the string models. And to my best knowledge, there are no counterexamples to these criteria within string models. But now, for the aim for the scope of this talk, let me try to be more precise on what this landscape of consistent theories should be. And to this end, I will show you one screenshot from the famous review by Palti, which defines the Swampland as the set of apparently consistent effective field theory that cannot be completed into quantum gravity in the ultraviolet. And right after, there is a note that in this definition, what one uses is the general notion of quantum gravity rather than specifically string theory. And this, I think, is related to the real core message of the Swampland program, that these Swampland criteria should be universal, in a sense. It should be a universal consistency criteria. And therefore, so for the scope of this talk, let me distinguish between two different notions of landscape. What I call Palti's landscape, and I mean, this is not the notation that we used in the paper, and probably it's not the best way to call it, but just I think it is useful to distinguish it from the string landscape to avoid confusion and to make the motivation and the concepts behind our work very clear. And so I define Palti's landscape really as the complement to the Swampland, so the space of all consistent effective field theory minus the Swampland. And the string landscape as the part of Palti's landscape associated with UV completion is stringy. So this part of the landscape with UV completion comes from string theory. And it is an extremely interesting question to understand how these two landscapes compare. So do they overlap in particular? And this question has been translated recently into the so-called string Lamppost principle. So the conjecture that all consistent quantum theories of gravity are part of the string landscape. So in a sense that the Palti's landscape and the string landscape coincide. And so far this has been tested within using string models. And it seems that all string models indeed belong to Palti's landscape, but these are in a sense unilateral tests of the Swampland conjectures. Since all quantum gravity models that have been tested come from string theory. And now the idea of this talk is very simple, and it is that of testing the Swampland conjectures within other approaches to quantum gravity. And in particular, the focus is asymptotically safe gravity. First of all, because I come from this approach, and second, because within asymptotic safety, which is written in the language of quantum field theory, is very easy to connect with effective field theory. And this might not be true in other approaches, or in that case, in the other approaches might be much more difficult. And we will also use the simplest possible setup. And the reason is that we simply want to provide with this work a proof of principle. And we wanted to focus on any conceptual difficulty without being overwhelmed by difficulties coming, for instance, from the numerical integration of the beta functions. So we simply took the simplest possible model to test the approach. And in principle, there is a lot to learn, because depending on whether the asymptotic safety landscape and the stringy landscape are disjoint, or for instance, the asymptotic safety landscape is a proper subset of the stringy landscape, this could have important implications. So for instance, it might hint at the possibility that asymptotic safety is a low energy approximation to some string models. Or if they are completely disjoint, they are perhaps incompatible. So I believe that this is, in my opinion, an interesting direction to explore. And independent of this, this would provide a non-trivial test of the string Lamppost principle. So now this is the motivation, but now believing that you are not all familiar with the framework of asymptotic safety, let me summarize what are the key points of the program. And in a few words, asymptotic safety is nothing but a non-perturbative generalization of the concept of asymptotic freedom. So in the case of asymptotic freedom, the running of the coupling with the energy scale brings the coupling to zero in the ultraviolet, or in terms of renormalization group trajectories in the Fourier space, it means that the RG trajectories approach the origin of the Fourier space, namely the Gaussian fixed point. While in the case of asymptotic safety, the couplings approach an interacting fixed point. So at high energies, they approach a finite non-zero value. And based on this concept, Weinberg in the 70s conjectured that gravity might make sense as a quantum field theory if it is non-perturbatively renormalizable with respect to an interacting fixed point. And this has been tested using different methods. So there is no formal proof, but some evidence. And there is evidence from two different approaches. So lattice-like computations within the causal or Euclidean dynamical triangulations program, in particular the causal dynamical triangulation, which seems to point to the existence of a second-order phase transition, and semi-analytical methods that use the so-called exact renormalization group, which is the favorite tool of the asymptotic safety community. Now, let me also spend 2 words about this method. So it is based on the functional normalization group equations. Solving this equation exactly essentially is equivalent to solving the path integral. And let me also say that this equation, in principle, as it is written, is exact. But in practice, in practical computations, some approximations have to be employed. But now the concept is that this object, gamma k, is a scale-dependent version of the ordinary effective action of quantum field theory. And so if one is able to solve this flow, essentially the fixed point of these equations correspond to the Bayer action of the theory. So fixed points with a certain number n of relevant directions. So the smallest is this number, the more predictive is the theory. And this corresponds to the Bayer action. And ideally, one would like then to integrate out the flow from the ultraviolet to the infrared. And in the limit where k goes to 0, one recovers the ordinary effective action of quantum field theory. And there are obviously infinitely many terms in principle, but if the RG trajectory is connected to an ultraviolet fixed point, this guarantees that these infinitely many terms are parameterized by only n free parameters. And obviously the effective action then gives access to observables, comparison with Wilson coefficients of effective field theory, S matrix elements, and so on and so forth. And now, given that I have given you enough motivations and I hopefully enough background, let me now present what would be the recipe at the basis of our work. And so the recipe in principle is general, so it can be applied to other systems. The ingredients are specific of the work with Ivano that we put out last year. So the recipe would be to take an action, a truncation, potentially in asymptotic safety. And in this work, we just take the simplest possible model that is relevant to compare with Swampland criteria. Then run the renormalization group machinery. So compute the beta function, compute fixed points, and then solve the beta functions such that one is able to connect the UV fixed point with a set of infrared points that constitute the asymptotic safety landscape. And these are connected via the RG flow. And then one can use the same set of Wilson coefficients to identify Paltis landscape. So the set of effective field theories that are compatible with Swampland criteria, a set of Swampland criteria, those that one can use, and find intersections, essentially. And now the ingredients of this specific work are a model of a one-loop quadratic gravity. And this is the simplest possible model that we could use to have essentially the possibility to test a reasonable number of conjectures and have to do with beta functions that are reasonably solvable numerically. And as Swampland conjectures we test, we used the Resistor conjecture, Transplanckian conjecture, and the weak gravity conjecture. The model, as I said, is quadratic gravity, and we use beta functions at one loop. So one has a Lagrangian that has the Einstein-Hilbert action plus quadratic operators, C square, R square, and Gauss-Bonnet. The couplings in this action are lambda, omega, theta, and obviously Newton coupling and cosmological constant. But these are all can all be written in terms of three-dimensionless couplings that are G lambda, GR, that is the coupling to R squared, GC, that is the coupling to C squared, and there would be also the Gauss-Bonnet coupling, but this turns out to be completely decoupled from the system. So practically, it is not really necessary to account for it in at one loop. And so the beta functions and the fixed point have been computed in this paper by Alessandro Codello and Roberto Percacci in 2006. It is a one-loop, simple, plain one-loop computation in quadratic gravity. And already here, one sees the presence of two fixed points, in particular, one of which can serve as our UV completion within this simple model. And I'm not showing you the beta functions since not a lot can be learned by just looking at them. But so the next step then is to take the beta functions and solve them to integrate the flow from the UV all the way down to the infrared, and finding essentially all infrared points in the space, in the Fourier space identified by these free couplings that are connected with the UV fixed point. And we have done this numerically, and all the blue points that you see here are the infrared points of asymptotically safe normalization group trajectories. And it turns out that they are placed on this plane that is given by this equation, and they all sit in the part of the Fourier space that corresponds to a positive GC, that is the C square coupling. And at this point, the idea is to compare this plane with the plane, the corresponding plane identified by some of the Swampland conjectures, some of the Swampland criteria. And of course, I will not really spend time on explaining the Swampland criteria since you know them better than me. But as for the weak gravity conjecture, this is essentially related to the condition that black holes remain subextremal. And the important bit of this is that once one adds higher derivatives to the action, this condition gets some corrections. And the correction to the extremality condition is written in this way. So it is related to this parameter delta that depends on the higher derivative couplings, and in particular C2 and C3, and it is parameter xi. Now this coupling C2 and C3 obviously can be written in terms of the couplings that I have shown you before, that are the coupling GR to the R square scalar, which is scalar square term, and GC, that is the coupling to C square, Y square. And translating this condition, that is assuming electromagnetic duality, the condition, the weak gravity conjecture essentially says that this quantity has to be positive. And in terms of our coupling, this essentially turns out to translate into this condition that GC has to be positive. But as I have shown you before, this is essentially already satisfied by the asymptotic safety landscape. The case of the de Sitter and Transplanckian conjecture is less straightforward. So first, the de Sitter conjecture is the condition that in any effective field theory that is consistent with an ultraviolet completion of gravity, if there is any scalar degree of freedom with a potential V, then its gradient has to be bigger, and here there is a typo, this should be bigger than the potential V. And therefore, for any critical point where the gradient of V has to be is 0, the potential is negative for some variations of the field of the order of the Planck mass. And the de Sitter conjecture is stated in terms of these two parameters, free parameters, F, C, and F, that are stated to be of order 1. And since this is not a precise condition, we also checked how this works for different values of F and C, including one specific value of C that is given by this relation, which essentially corresponds to the Transplanckian conjecture and is relevant for early universe cosmology. But now, in terms of our action, the way the scalar degree of freedom arises from the higher derivative part of the action, in particular from the R square term. And indeed, in the Einstein frame, the type of action translates into Einstein gravity plus a scalar degrees of freedom subject to this potential. It is essentially a Starobinsky-like potential where the inflaton mass is obviously related to the R square coupling. And this translates in non-trivial bounds for different values of F and C. And so we tried to check these bounds for different values of these parameters. And as you can see, so they are plotted in the GR and G lambda plane. This corresponds to small value of F, and this corresponds to F equal to 1. And for lambda negative, so first of all, let me state that the colorful regions are those that are compatible with de Sitter or Transplanckian conjectures. And for lambda less than 0, most of the time the conjecture is satisfied, but it is also non-trivial because depending on the value of lambda and the GR, this potential does not always have a minimum. So it is really non-trivial how this interplay works and how this how the practical realization of these constraints in this plane. And now we can finally put everything together and try to visualize the intersection between the asymptotic safety landscape and the Baltis landscape. And I'm showing you like 3 different orientations for this 3-dimensional plane, because it is obviously difficult to identify this intersection. So now the green plane is the asymptotic safety landscape. And as I told you before, this is fully within the yellow hyperplane that corresponds to the weak gravity conjecture. But there is a non-trivial intersection with the blue hyperplane that corresponds to the de Sitter or Transplanckian conjecture, simply because you should think of this hyperplane, so this 3-dimensional space for say the hyperplane corresponding to the TCC is the 3-dimensional version of these 2 figures once one allows this to hold for any value of a GR. And so there will be some tiny region of the Fury space, and in particular of the asymptotic safety landscape, where the TCC and the de Sitter conjecture do not hold. So there is a non-trivial intersection. But again, one should keep in mind that this is a very simple model where we took just one loop approximation, quadratic gravity, and only some Swampland conjectures. One, of course, should improve the computation, should make it actually precise. Indeed, and this brings me to my conclusion. The idea of this work was to provide a proof of principle, the proof of concept that one can, and it is interesting to test Swampland conjectures in other approaches to quantum gravity. And in particular, this is doable in the context of asymptotic safety. And the recipe is clear. So one just take one model of asymptotic safety and integrate the RG flow from the UV all the way down to the infrared, and attempt to find the intersections between the asymptotic safety landscape and the landscape identified by Swampland criteria. And in our toy model, we found a non-trivial intersection. It is somewhat funny because it is difficult to interpret. It might mean that asymptotic safety is wrong, Swampland criteria are incomplete if this would hold in a more precise setting. But in general, I mean, in a more precise computation, this would, so that depending on the result, one could come up with different conclusions. So for instance, if the asymptotic safety landscape is completely disjoint from the stringy landscape, the 2 approaches will be incompatible. But say that the asymptotic safety landscape is within the stringy landscape, one could, this could be seen as an indication that asymptotic safety perhaps is a low energy approximation to a string model. And this has been suggested already in a couple of papers. And of course, in this research line, so there are some obvious generalization can be done and in-depth studies. So for instance, as I said, this work was just based on a one loop approximation, and this is simply because functional normalization group computations are extremely tough to perform. And so for instance, the full R-square truncation has been worked out only recently last year by Benjamin Knorr. And together with him, we are now trying to work out the full quadratic order in the gravity plus U1. This stuff, but I mean, this will allow later to investigate in more detail how the weak gravity conjecture bounds look like in asymptotic safety. And there is more that one can do, for instance, by investigating no global symmetries, whether this is compatible with asymptotic safety, something that I discussed with Ivano, Vasile, and Benjamin Knorr recently, even though we still have to set up computations practically. And in general, in the spirit of cross-fertilization of approaches and attempting to exploit the strengths of different approaches, there is also another research line that I'm pushing with Ivano that is about exploiting the functional normalization group in string theory to compute alpha prime corrections, simply because, I mean, even if the two could kind of improve, take the best of both approaches, since because of stringy symmetries, since string theory is more constrained than asymptotic safety, in some cases the FRG can be applied exactly to these systems. And I think this is, in my opinion, an interesting direction to look at. And so I leave you with this picture, and I thank you for your attention, and I'm looking forward to your questions and comments.
Let's give a big round of applause. Thank you, Alessia, for the wonderful talk. Even though we're a bit late, but we have some time for questions from the audience. So maybe while we already have a question. Okay. Yep, Ling.
Hey.
Yep.
Hi. Thanks for the talk. Very interesting. I have a question though. So in this, even if you say you pick a toy model, from your starting point, are there? Maybe I missed it, but are there any kind of selection criteria that you put in to say pick your parameter in the that defines your asymptotic safe model? Because I mean, the one aspect, right, of the swampland idea is sort of that what you would naively expect from a field theory perspective of how you define your high energy UV completion is actually not consistent. So my question here is, since you have showed this picture where there's some disagreement, yeah, are there any kind of restrictions you put, or are you just sort of trying out all the parameters that from field theory can define your UV point?
So I'm not sure I fully understand the question. So you are asking essentially, how do I choose an action, right?
Yes.
Okay. So the point is, in principle, one should consider all possible operators and study the flow of all of them, which is of course tough. Mm-hmm. And there are different ordering criteria that one can use. So expand the action in some way and then truncate that to a certain order. So for instance, one can use a curvature expansion or a vertex expansion or a derivative expansion and truncate to a certain order. But so one of the things that has been seen, like if you want a posteriori, is that one once one so when one does these computations, one tries to first find the fixed point and also see what are the critical exponents associated with the different directions. And this is important because, well, first of all, you identify the number of relevant directions. And the second, you have an estimate for the anomalous dimension that is associated with each operator, with its coupling. And one can see a posteriori that if you order the contribution according to their canonical mass dimension, one can also see that the anomalous dimension associated with every coupling is smaller and smaller as one increases the truncation order. And therefore, one can see a certain type of apparent convergence. So if you include more and more operators, the critical exponents and the fixed point values approach they go to saturation, so they approach they seem to be stable. So different computation have been done. So for instance, in the case of F of R like theories, people have computed beta functions up to the order 77, if I remember correctly, which is, impressive. And it seems like results are stable.
But now you're trying to go from the IR into the UV, sort of re-evaluate what kind of UV fixed point you can have to give you certain IR parameters, or what is that computation that you just described, this convergence? Is it a convergence into the UV?
Convergence in the sense that universal quantities, so of course, in an RG flow, there are certain features that are universal. For instance, the infrared and the critical exponents. Mm-hmm. And other features that are simply not physical. So for instance, exactly what are the RG trajectories between the UV and the IR. So when one does this type of computations, so one computes these universal quantities and then increase a little bit the dimension of the Fourier space and see what happens, and then increase it one by one to see if there is any type of convergence for the values of universal parameters.
Okay. Okay, maybe I'll let Matilda ask first, and then I might come back to. Thanks.
Hey, hi Alessia, thanks for the very interesting talk. I was just curious about one thing. So this F parameter that you introduced, it tells you about the distance that you're traversing in field space, right?
Sorry, I cannot really hear you well. Can you maybe come closer to the microphone?
Yeah, sorry. I was wondering about the parameter F. It dictates how far you're going in field space, right? Mm-hmm. So, yes. So the Resistor conjecture at least is usually expected to hold for large F then, right? I was wondering if then the comparison, the intersection that you have between the asymptotic safety results and the Swampland results, how does that change when you vary F? Do you have somehow more overlap when F is large, or?
So the Resistor conjecture I'm aware of as an F that is order 1, but yeah, obviously. So there is some change when one changes F, in the sense that, so for instance, if you compare these two plots that are for same range of C, but different values of F, so you can see that once F gets larger, there are the region where the Swampland criteria are not satisfied is also tends also to be larger. So I would say there is still a non-trivial intersection, but how large is the incompatibility region depends on F and also on C.
So does it get larger with? Do you know? Maybe you don't remember, or I can look at the paper. But do you have a notion of if the intersection gets larger with F equal 1, or is it larger with F equal 0.1?
So the intersection is larger with the standard landscape when F is small.
Okay.
I would say, or at least we have checked only a few values of F around order 1, but things could be nonlinear. So I don't feel like making any statement about the large F. Okay. But if you say that so the regime of large F could be interesting, maybe can you forward me the paper and I might have a look at it.
Yeah, no, I'll also take a look at your paper to make sure.
Okay.
Thanks.
Thank you.
All right. Thanks so much for your questions. Let me remind you that there's this very nice, well, let me stop the recording now, since we are way over time. And let me remind you that we have this very nice Slack channel